Hi everyone, welcome back to Automata, Grammars, and Computability. Today, we are on regular expressions and Thompson's construction. So we have the definition that a finite machine M recognizes a language A if A is equal to the set W such that M accepts W. So a language is a set of strings. In this case, it's the set of strings where M accepts W. Now, on top of that, we can say that a language has a certain property that it's regular if a finite automaton recognizes it. Right? Let's break this down a little bit more and look at an example. So the set W such that W contains a string 1, 1 is a language which is regular because I can draw it as this DFA right here. And it turns out that the set notation that I have, W such that W contains substring 1, 1, and the DFA that I've drawn are equivalent. So this M1 is a DFA, has a language associated to it, and that language is what's called regular because I can draw this picture. On the previous slide, I showed set notation and a DFA diagram, and those were two different ways of representing the same thing. It happens to be the case that I wrote a DFA or drew a DFA, but I could have also drawn an NFA for it, and it turns out that NFAs and DFAs are equivalent, right? So any NFA can be transformed into a DFA and vice versa. Now, that seems good because we now have different ways of representing the same thing. And we also have set notation. Now, it turns out that we have one more way to describe languages, but specifically regular languages. So we can use regular expressions to describe regular languages. Regular expressions can be written as NFAs, so they're equivalent to NFAs and DFAs as well. I like set notation, but set notation is very expressive and it can describe languages that are non-regular. We'll talk about that more in a little bit. Right now, the point I want to get across is that there are different ways to describe a language, but NFAs, DFAs, and regular expressions can only be used to describe languages which are what are considered regular. Before we move on into talking more about regular languages, I want to talk about the symbol star and specifically sigma star. So sigma, as we have seen before, is an alphabet of symbols. So usually the examples might be like the binary string, like 0 and 1. The alphabet is 0 and 1. And now I've appended the star to the end of it. What does that mean? A star, or Kleene star, means it's 0 or more repetitions of whatever's to the left of the star. So sigma star represents all of the possible words over the alphabet sigma. So the empty word is just epsilon, we would write to say it's a string of length 0. One-letter words are just literally the letters of the alphabet. You can have two-letter words, X, Y, so every pair, where X and Y are both alphabet letters, and so on. So sigma star is there to show you basically all the combinations of letters that you can have over the alphabet sigma. So the star represents 0 or more repetitions of whatever's to its left. In this case, I've written sigma, so sigma is all of the alphabet. Another way to describe sigma star, which is sometimes useful, is that it's equal to the union of I greater than or equal to 0 of sigma to the I, where sigma is the set of strings over sigma of length I. So looking above, one-letter words are just going to be I is equal to 1. sigma to the 1, or just sigma. 2-letter words would be sigma to the 2, and so on. Right? So this slide is here just to introduce you to the character star and to know what it means in context. And with this starting to make sense, we will be able to talk about regular expressions and regular languages a little bit more. To understand better what sigma star means, let's look at some examples. I have 2 examples here. So A, B, and C is going to be sigma in the first example. So the letters A, B, and C are what make up my alphabet. And the second example I have is 0 and 1, which is probably the most common alphabet we're going to see as computer scientists. So I recommend pausing the video and writing down some strings that have A, B, C as the alphabet and 0, 1 as the alphabet. I'll show some examples in a moment, and they probably won't match what you have, but that's okay as long as you have some examples that make sense. It means that you're starting to get what is meant by sigma star. So the first example I have is ABCA. So the letters A, B, and C are all used, and I have, I just picked them, and I have this string, which is of length 4. I have B, C, B, C, B. In this case, I did not use the letter A. I have a string of length 5. And then finally, I have A, B, A, 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 A. So here I have used only the letters A and B, and I have many repetitions of the letter A. Okay, but these all use only the letters which are in the alphabet ABC, so they are examples in sigma star. My examples for 0 and 1 are going to be a little bit more general. So rather than just writing some strings, I'm going to point out that 0, 1 has all binary strings, and 0, 1 to the I means all binary strings of length I. And here I am saying that 0, 1 star is equal to the union of I greater than or equal to 0 of 0, 1 to the I. Okay, so here what I've done basically to show you sigma is I've replaced the letter sigma with 0 and 1 because that was the alphabet, and it's still in set notation here. So rather than writing sigma to the I have written 0, 1 in curly braces to the I. Okay, so those are some examples of sigma star over 2 different alphabets. And hopefully this is becoming a little bit more clear to you how that star is going to the thing to its left and just taking out basically as many repetitions of letters as it very well pleases. So now that we understand Kleene star, we can start talking about regular operations and expressions. If we have 2 languages, A and B, we can do certain things with them. We can take the union of 2 languages. A union B is equal to the set W such that W is in A or W is in B. We can do something called concatenation, which is generally represented by this dot, but you actually don't have to write it. It's the combination of X then Y for all X in A and Y in B. And then Kleene star. So we've seen the star before associated to sigma. In this case, I'm doing star to A. And so basically, that means that I'm going to take out words in A, and I'm going to just like grab as many of them as I feel like, and that's what's going to make the Kleene star of it. So when we have a regular language, it's actually built up of regular expressions, which are built from sigma itself, so the alphabet, and consisting of the letters of sigma, the empty set, and the empty string. And then once you have individual letters, you can start building up more words. And so that's where you're going to use union, concatenation, or star to build up more complicated languages. And it turns out that all of the languages that we are writing that are regular can be written either as these atomic expressions, like just letters or empty, or the union, concatenation, or Kleene star of smaller languages. Just to reiterate, regular languages are closed under the operations of union, concatenation, and Kleene star. So we saw that before in the previous slide, where you can take two regular languages, union them, you'll still have a regular language. It also turns out that you can take the complement of a language and you can take the intersection of two languages and still have a regular language. So let's look at some regular language examples to get a sense of union, concatenation, and Kleene star. Let's say A is the language which has the words good and bad in it, and B is the language that has boy and girl in it. You can union A and B. Now I have the language good, bad, boy, girl. I can concatenate, which basically takes every pair. So since I had 2 words in A and 2 words in B, I have 2 times 2, or 4 words. Good boy, good girl, bad boy, bad girl. A star, which is just by itself, is going to have epsilon, which is the empty string, 0 repetitions of good or bad. And then it'll have good, bad, which is an A anyway, and so on and so forth. So I can have good, 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 bad, bad, good, bad, bad, good, good, good. And this will just keep going. And one thing you might notice here is A was a finite language. It only had 2 elements, but A star has infinitely many elements in it because you can just keep repeating the elements as many times of good, bad as you want. Let's look at 3 examples of regular expressions and then describe what they are using words. So 1, I have 0 union 1, and it's all in parentheses to the star, which is equal to sigma star when sigma is 0, 1. Sigma star concatenated with 1, and sigma star concatenated with 1, 1 concatenated with sigma star. So let's take a moment and just think about how you would describe what these regular expressions mean using just normal English. The first one, since it's 0 union 1, that's the whole language. There's only 2 letters, but I'm going to take it to the star, and it's equal to sigma star. So this is going to be all strings that are possible over 0 and 1. Or you might have written all binary strings. The second one, sigma star concatenated with 1, these are all strings, binary strings, that specifically end with 1. And then finally, I have sigma star concatenated with 1, 1, concatenated with sigma star. Those are all strings that contain 1, 1. One thing you will see if you read Sipser is that there's kind of a formal way to write regular expressions, which is the theoretical way usually to write it. But regex, or regular expressions, are very important to things that you would do on your computer in your terminal. And so the way that the formatting for those things go is a little bit different than what you would write in theory. So this table is just here to describe what that would look like. And so the whole point of this is to just show how the notation can be a little bit funky. Whereas we are writing A union B to say language A or B, here I have A and then pipe B for the regex of it. Concatenation is actually not too bad. It's the A circle B, which is equal to AB, and then luckily in regex it's just AB. Cleany star similarly, A star and A star. There are other set operations you can do, like A intersect B or not A, but they're not necessarily available in the regex languages libraries that you may use when you are doing any sort of coding or looking for files. And then, of course, because these are regular expressions, there are equivalent NFAs for it. One thing we're going to talk about a little bit more in depth is how to draw the union and the concatenation and the Cleany star of the from the regular expression to draw the NFA. You can use subset construction from there to go from NFA to DFA, but it's not straightforward. In fact, normally it's not so easy to draw the DFA, but one thing that's nice is if you do have the complement of a DFA that you want to draw, you just flip the accept and reject states. Now that we've seen notation that shows kind of the theory way to write things, and then also regex, the way you would write it if you were closer to something that you would do on the terminal, let's look at some examples. The big change here is that we now have this pipe instead of using the union sign. So that's where, let's work through these examples. You'll see that I have these pipes here. And so one way to think of the pipe is union, but another way that you may already be thinking of is that it could represent OR. So this first string is going to be 0 or something else. And so the string 0 is included, and then this other thing is included. And let's work through what this other string is. I see that it ends in 0, and then it starts with 1. And then this is 0 or 1 star. So in other words, any binary string that starts with 1 and ends in 0. So let's take a moment to think if the strings that I can have are either 0 itself or any other string that starts with 1 and ends with 0, what's like another way to write what that string is? Take a moment to think about that. And it represents all even binary numbers because this is all strings that end in 0. Okay, so every time we write these regular expressions, you can go from a regular expression to some sort of description. Usually that's something nice. But you could also start with this description, all words representing even binary numbers, and write a regular expression from it. So take a moment, pause this video, and see if you can write down a decent description for each of the remaining examples. So moving on, I see in the second example, I'm starting with a 1 and I'm ending with a 1. And just like above, I have that 0 or 1 star. So 0 or 1 star, by the way, could also have written as 0 union 1 star, as we saw previously. But for regex, we're writing with a pipe. But so we see that this is going to be 1, any binary string, and then ending with 1. So these are all words that start and end with 1. In the next example, I again have 1 and 1 at the beginning and the end. But this time, in the center, I don't have 0 or 1 star, I have 0 star. And star is going to bind to the thing to its left. So it's going to be 1, and then any number of zeros repeated, and then a 1. So these are all words that start and end with a 1 with only zeros in between. Okay, so hopefully that's starting to become a little bit more clear as to like what these expressions are denoting. Let's continue. I see again I have an OR, and it can be 0, or it can be 1, 1. And now I have a star after that. Let's think about this for a moment. Another way to write this would be 0 union 1, 1 star. And so basically, this means that I can have either 0 or 1, 1 repeated as many times as I want. So these are all words consisting of any combination of 0 and 1, 1. Another way to write this, if it helps you to make sense of it, you could say 0, 1, 1. Here's my set taken to the star. Final example, I have 0 or 1, or 1, 0, or 1, 1. There's no stars or anything, so it's literally just 0, 1, 1, 0, and 1, 1. That's the entire language. The last example that I had on the previous slide is equivalent to the DFA that we talked about earlier in this video. Sigma star concatenated with 1, 1 concatenated with sigma star. Let's take a look at why this DFA is equivalent. First, I have sigma star. So that means 0 or 1 repetitions of any number of strings with 0 and 1. I have 0, and as long as I'm reading 0, I will stay in Q1. And then if I read 1 and then 0, I will go back to Q1. Next, I have 1, 1. So I'll see the second that I see 1, and then another 1, I can go forward into Q3. And then at the end, I have sigma star. So I've already accepted this string, but I can have any number of zeros and ones after that, which is what this last part indicates. So this is how you can see that this happens to be a DFA that's equivalent to the regular expression. Hopefully at this point, you're starting to believe that NFAs and DFAs and regular expressions are equivalent. But if you're not yet convinced, Thompson's construction can help you with that. So Thompson's construction is a method of transforming a regular expression into an equivalent non-deterministic finite automaton. And from there, you could go from that NFA and turn it into a DFA. The steps of Thompson's construction are as follows. First, the user, probably you, is going to enter a regular expression using regex notation. So we've seen the pipe and the star and just not putting anything for concatenation. Now, a program like egrep will parse the regex and construct an NFA out of it. It's going to take each small part of the regex, basically everything that's not one of the symbols, and it's going to produce an NFA out of it. Those NFAs are going to be combined using star and union and concatenation to produce a larger NFA. And then at last, there's going to be one NFA for the entire regex. At that point, grep can either simulate the NFA directly, or it's possible to convert the NFA into a DFA. And you will remember that we talked about both these atomic parts to the language and the composite. So just try to take a moment, pause the video, think about what the atomic parts of a regular language are, and what were the composite parts. The atomic parts that we had were either the empty expression or a symbol that was in the alphabet. So if you don't have anything at all, you can just do an NFA that just takes an epsilon transition and goes to a final state. Now, if you have a single symbol that you want to be able to read from the input alphabet, you can turn it into a single arrow that goes into a final state. Now, if I have that and I want to do something like A or B, basically two symbols of the input alphabet, I can combine these two. I recommend trying to think about how I would use the epsilon arrows and then trying to take the union, recognizing the language A or B. The union expression is S or T, and it basically takes the epsilon transitions that we saw, and it's going to make it so that you can either go towards an NFA for S or an NFA for T. That's what these epsilon transitions allows you to do. It allows you to take that or. And basically, these epsilon transitions are going to go into the initial states for NS, do whatever needs to happen here while reading the expression, and then go to the final state for F, which should be an accept state, and then you can take an epsilon transition out to accept the word. Similarly, inside N of T, you're going to have your initial states that it goes to, and then finally this final state, which should also be accept, and it will go to the final state to accept. Okay, this thing might be a little bit bigger than is needed to actually describe the union expression S or T, but it's a pretty, it's like the quickest way to draw the union expression. Now we're going to think about concatenation. What about something that starts with S and ends with T? How do you accept that? The concatenation expression looks like this. So S then T. The initial state of the NFA that goes with S, N of S, is the initial state of the whole NFA. The final state of N of S, maybe writing like this will make it clear, becomes the initial state of N of T. And the final state of N of T, which is right here, becomes the final state for the whole NFA. So basically, we're just going to read all of the states for S concatenated with T, and then draw arrows out to the start of N of T. Then finally, we have the Kleene star expression, which is S star, any number of repetitions of S. So you'll notice here that we have epsilon transitions because I can have 0 repetitions. So I can go epsilon and then whatever happens inside N of S, which from the final state of N of S, it'll take an epsilon transition back to the beginning. If I have 0 repetitions, it'll just go straight to the final state. In the end, the final state of inside N of S will also be able to do an epsilon transition to the final state overall of the whole thing. This is all Thompson's construction is just taking the 3 things that we had, which was union, concatenation, and Kleene star, and then drawing new NFAs for it. And once you have these NFAs, you can convert them into a DFA. And thus that shows us that DFAs, NFAs, and regular expressions are equivalent. Just to sum things up, we can denote a regular language using a diagram of an NFA or DFA. We can use set notation because a language is a set of string. We can use something called a regular grammar, which we'll talk about more later. We can use regex notation, which is what we've seen today, or regular expressions. Regex is used in many programming languages such as Java or Python. Sometimes the notation looks a little bit different than what we've seen here today, but all of those things should have meanings associated to them that you can look up in their libraries. And also you can use egrep at the command line to search in your file system. One thing I do want to point out, if you do have like a DFA or NFA, you can write set notation for it. Set notation, however, is more expressive than regular expressions or DFAs. So set notation can actually describe more complicated language than those that we can draw NFAs and DFAs for. We'll talk about that more later. Let's talk about regex a little bit more, just to get a handle on it. So all of this I did with VS Code, by the way. So I just open up a text file to do this. I have Wordle, and I'm going to use my text editing powers to help me win the Wordle here. Let's say I went ahead and I guessed the word slate, and then I guessed the word wretch. And now I know from my dictionary that 103 words have the letters E, T, and C in them. But I actually have more information than just words that have E, T, and C in them. I know that I can remove all the words that have a C in the fourth position or have the letter A in them. I can remove, let's see, I can remove the letters S, L, A, and R, H here. And I also know about some positioning. So let's use that information. Notation that we haven't seen before is dot, but dot represents a single character. So what I've done here is I did a find and replace in VS Code, and I have this dot star option on, and you'll see that I've written dot 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 C dot. That's going to match all words that have the letter C in the fourth position, because each dot represents a single character. This is kind of like this capital sigma. It's just that I only have, I don't use the letter sigma. I don't have it on my keyboard, so I'm going to use dot. And then here, I'm going to replace, I'm going to remove all the words that have A in them. So that's going to be dot star A dot star. And remember, star binds to the thing to its left. So dot star means the same thing as sigma star. So dot star A dot star finds all words with an A in them at all. And I'm just going to go through and I'm going to remove all these words. Another way to do this is you can put in parentheses dot star, so parentheses dot star close parentheses. You can use that to make it easier to read, but in this case there's only a single symbol, so it's not necessary. I know the letters R, H, S, L, and A are not in my final answer either. So I'm going to do dot star and then just R or H or S or L or A in parentheses and then dot star. That's going to remove all words that have those letters in them at all. And you'll see here I'm using the pipe to show or union, depending on how you want to think about it. Now, with all of that work done, I'm left with three things: civet, comet, or covet. There's only three possible words left. And so at that point, I just kind of have to guess. So I just will. And I'm going to see, well, I got it in 4 because it wasn't comet, it was covet that day. So that shows you an example of how you can use regex to do find and replace. And this is something I did using VS Code and Wordle, but it's something that you would probably do at your terminal or possibly when you're writing some sort of program. And that's all I have for you today. So thanks for watching.